You recall in the last video we had a look at the flags and we determined that none of them showed any incorrect data we need to worry about. Before we go along to do some more, data cleaning, I wanted to go back and look at one important thing. So, and I think I mentioned this in the video, that the way that we did this was that we read in the information from the lines in the data file, and we read those into lists, and then we converted those lists to NumPy arrays. So these are our lists, and when we wanted to do our element-wise operations, we converted that list to a NumPy array so that we could use the NumPy methods. Now we can do that with all of those lists, but I wanted to talk about why it is we did it that way, and what are the alternatives and what the implications of those alternatives are. So to see why we did it that way, we need to have another look at the way that data from arrays and lists is stored within the memory. So we need to talk about data again. Now, as it points out here, we could have accumulated the data directly into arrays. So NumPy has an append method, which will do that. There's an example here, appending the arrays together to get a new array. So why didn't we do it that way? Well, we could have done it that way, but actually it would have been a lot more computationally expensive. And to see why that's the case, let's have again a closer look at the way that arrays and lists are stored. To see why it's more efficient to accumulate a list rather than an array, let's go back to our diagram from Van der Plas. You remember that we talked about the fact that for an array we knew that it's homogeneous, so all of the items in that array are all the same size, and we can stack them together very efficiently in memory. Now remember that this part of memory shown here is just part of a much larger memory, and that memory is being used for other things. So it's being used for other things by our own program. We might be storing other variables, for example. So we might want to store another variable that's put in here. It's being used by the notebook, it's being used by the operating system. Some other process altogether might store something in here. Okay, so what happens now if we want to increase the size of our array? So we want to add one more thing to the array. Well, we've got a problem, because the next position here is already taken up by something else. Okay, so what we actually need to do is we need to move the whole array. So we need to find, so let's say our memory continues over here, and we find another spot in memory that has enough room for 9 things. Okay, from 1 to 9. And then we're going to have to copy all of those things over. So we copy this item over, and so on, up to the 8th one, and we can put our 9th one in here. So that's a very slow operation. We could have a million things in this array, and we've got to copy all those to a bigger location to allow for the extra data. Now we can get around that a little bit. So for example, we can make our language or our operating system so that it allows a bit more room for fixed size arrays. So rather than just 8, we could allow for say 10 items, or we could allow for double, say 16 items. But it's not really going to help us in the long run, because even if we have enough room there for 10 and we keep these two empty, that'll save us for the first 2 things that we add, but the next one we add, we're still going to have to copy them all to a new location. So that's very inefficient. If we look at our list, on the other hand, our Python list, remember it was a heterogeneous list, and we stored our items in memory somewhere, and we pointed to them from our catalog or our index here. So let's say again that this is part of a larger piece of memory, and something else has used this bit and something else has used that bit, and we want to add a new item to this list. Well, we can do that just by adding it in, say, here. We just need to find enough room now for the item, not for the whole list. Okay, and then we can point to that from our index and store the new item in the list here. Then we want to add another one again. So this could be our, let's say that's our 9th one. We want to add our 10th one. We could put it up here and get our index to point to that one. Okay, and store our 10th item in there and so forth. And we can keep doing that. We only have to keep finding a little bit of space in the memory, enough to store the new thing that we want to add on, because it doesn't really matter where these things here are stored, because we only ever access them through our pointers to those items. And we don't even have to necessarily use this list structure here with these pointers. We can use something like a linked list structure, which actually has a pointer from the last item that we had in the list. So in this case, the last item is actually this one here, which is way up here. So we can have a pointer from that one through to the next item. Okay, we can have a doubly linked list where we can also go backwards in the list from this item to the previous one, and so forth. So there's different ways that the list can be done according to what's efficient for the purposes being used. But the main thing to notice is that you can add new items because it's a dynamic structure. We can add new items somewhere in the memory, point to the new item. We don't have to shift all the ones we've got. Whereas with the array model, we want to add a new item, we have to find more space and move them all. And so if we're accumulating a list of a million items, we don't just have to move all those things once, we have to move them a million times. Yeah, so we store, our first 100,000 items here, and then we've got our 100,001 item. So we've got to copy those whole 100,000 to a new location and add the next one in. And we end up doing a million, in the order of a million copies of a million things. So that's going to be really, really inefficient. Yeah, as I said, we can get around it a little bit by pre-reserving some space and so forth, but we can never fully solve that problem. And that's why it's more efficient to accumulate things using a list structure and then cast them to an array when we have the full list. If we know how big our array is going to be in advance, then we can reserve that space in advance, and we can efficiently put the array in. So that's what we'll have a look at next. So, as we saw, increasing the size of the array overflows the amount of memory that's allocated to that array and has to be copied to another place in memory with more space. And actually you can see a hint about that if you look at the small print for NumPy's append method again. So, so there's a note here. Note that append does not occur in place. A new array is allocated and filled with each append. So that tells you what we just looked at, that you get a copy each time. So it's a very inefficient way of doing it. So one more efficient way of doing it is using lists and then accumulating those lists. But in fact, we can do it directly to arrays, providing we work out in advance how much space we're going to need, and then pre-allocate that space, or effectively reserve that space in memory for the whole array before we start, so we don't have to keep building it and shifting it. Okay, so there's an easy way to do that. We don't need to get too much into the depths of memory. We can just use the array creation methods. We've seen these before, things like ones, zeros. There's another one called empty that we can also use that creates an empty array. So if we want to do that, then the first thing we need to know is we have to work out what size we want in advance. Sometimes when we have data, we have the dimensions with it, so we may know what that is. If we don't, we can find it out using Python. So for example, so remember this was our data file from the Fremantle measurement site, sea level measurement site. So we can just read it in, split the line, see how long that is. So that's one way of doing it. If we know a little bit about, and I remember I said in an earlier video that if you have some time, it's always good to learn a bit of Unix. So if we know a bit of Unix shell scripting, we can do something like this. The exclamation mark here just means we're going to execute a shell command, so it passes it through to the shell rather than executing it in Python. And you don't need to know the details of this, but this just is short for concatenate, which essentially lists this file, pipes it through to something called word count, and that tells us that in this file there is 1,476 lines, 4,000 odd words and 38,000 characters. So that tells us how many pieces of data there's going to be in each column. There's going to be 1,476. The size that's going to be reserved is determined by the data type. So it's a good time to have a look a little bit more closely at the NumPy's numerical data types. So it's worth spending a little bit of time on this. So this lists the data types available. So remember that we've been using int and float as part of Python, but we haven't been exercising a lot of control over how we store integers, how we store floats, what size memory we use for each of those. And in fact, there are choices about how you store these things depending on what size and what precision of the numbers that you want to store. If we have a look here, so NumPy numerical types are instances of D type or data type, and the 5 basic types available are booleans, integers, unsigned integers, floating point, and complex numbers. Within those, we can have a different size or number of bits that we use to store each of the numbers. So the ones that I'm going to use in this course are these ones here. So these ones at the top are primitive types, which are, if you use the language C, which Python's implemented in, it's a bit closer to the machine level architecture, if you like. But NumPy provides these ones that are independent of the platform, so independent of whether you're on, what computer you're on, whether you're on Windows or whether you're on a Mac or Linux or so forth. So these allow us to specify the type, whether it's an int, for example, or a float, for instance, and also the length, the number of bits that we use to store that type. So all of those type names can also be used for casting things into that type. So let's have a look at an example of that. It's probably the best way to see it. So the space for these types depends on the architecture, as I've said. You're probably using a 64-bit architecture unless you've got a very old computer. So let's have a look at start with some of what the defaults are. So let's say that we've got a numpy array and we make it from a list of integers, 1, 2, 3, and then we print the data type. Okay, so that tells us that by default of those types, remember there were a range of different kinds of integers, for instance. The default is to do it as an int64 or 64-bit integer. If we look at an example of floats, we'll see that the default for float is also 64 bits. As we pointed out when we were talking about creating lists before, we can also say, we can tell NumPy explicitly what type we want to use. So let's say we've got our integers again, and we can put the type. So let's say we want to store those as unsigned 8-bit integers. Then we'd use numpy.unsigned int 8, and if we again print out the d type, it tells us that it stored them as unsigned integers, 8-bit integers. So for most of this course we'll be using the default 64-bit numerical data types, but you need to be aware that there's other types, and some examples of those that you'll come across. In image processing, for example, typically a lot of the image formats like GIFs and PNG use 8-bit unsigned integers, which range from 0 to 255. String characters typically use UTF-8, which is 8-bit Unicode, or includes the ASCII codes. We can do an example of that. So let's say that this time we have, say, a okay, so that U1 refers to a 1-byte unsigned integer.